Today we'll talk about pressure at a point inside a liquid. At a previous session, we discussed the concept of pressure, where pressure is a physical quantity which connected between the applied force and the area which the force affects. Where if the force is great and the area affected is small, means the pressure will be great. But when the force is small, which affects on a large area, this force will distributed on a large area, so its effect will be decreased, so the pressure will be less. The pressure equals F over A. But now we'll try to find the factors affecting the force at a point inside a liquid. If we imagine a container contains a fluid, this container is closed and there is a point inside this liquid. This point at a depth from the surface of fluid equals h. If we try to find the pressure at this point, at first the point not area, so we'll find an area to this point. So we'll take 1 meter length and 1 meter width around this point. So the force acts, so the area, we find the area 1 meter square around this point, but what is the force affecting this point to make the pressure? The force affecting this point is the weight of fluid above this area, which make a column of fluid. So the weight of this column is the force which acts normally at this point. Okay, so we'll try to find the weight of this fluid column. If we substitute the force or the weight by mg, so pressure equal mg over A. But rho, the density of fluid, equals mass over volume. So the mass will be equals rho multiplying volume. So the pressure equals, we'll substitute mass by rho volume multiplying G over A. But the volume of fluid column here equals the area multiplying the depth or the height of this column. The volume equals A multiplying H. So rho AH G over A by cancelled A and A, so the pressure will be equals rho G H. Rho G H. The pressure equals rho, the density of fluid, G, the acceleration due to gravity, H, the depth of the point which we need to find the value of pressure at. So the pressure depends on the density of fluid and the depth of point. Because G is a constant, G equal 9.8 meter per second square, so its value is a constant, but rho and H is two physical quantities, has the ability to change according to the type of fluid. If we change the fluid, will it change its density? If we find the pressure at a point from the surface 5 centimeters, not equal the pressure at 10 centimeters. The pressure will change according to the depth of point. So the two factors affect the pressure at the point of fluid. P is directly proportional to the density of fluid, where the pressure increase if the density of fluid increase. The pressure is directly proportional to H, so the pressure increase when the depth of point increase. So high dam is built where its top less thickness than its bottom. Its bottom is more thickness than its top, because when we go down towards the bottom of the water, the pressure increase, so we'll need a building to prevent the pressure. So when we move downwards, the depth increase, so the pressure increase. But the relation between rho and H is inversely, where when the pressure is a constant, the points, if we have two fluids like water and glycerine, the points at the same depth, the points with the same pressure will be not equal in the same depth. Means the fluid which have more density has less depth to give the same pressure. But all points in the same fluids and the same horizontal level has the same pressure. Okay? If we have a fluid like water and have different points, 1, 2, 3, 4, and 5. where 1 and 5 in the same plane and 2 and 4 in the same plane. But 1, 5, 2, 4 and 3 has no the same level. Which point or points have less pressure? Because this fluid is homogeneous, so the density is a constant according to any point. So the density at 1 or 2 or 3 or 4 or 5 is a constant. And G is a constant. And G is a constant where H is different from point to another. Where H is small means pressure is small. H is a large means pressure is a large. So the less point in depth is 1 and 5. So 1 and 5 has the same pressure, has the same less pressure than to the other points. The largest point in pressure is a 3 because it has a large depth. So by increasing H, the pressure will be increased. But point 2 and 4 has the same pressure because they have the same density and the acceleration due to gravity, and they has the same H. At the end, we can find that all points at the same horizontal level has the same pressure. Why? Because the fluid is a homogeneous and have the same depth from the surface of fluid. Okay? This rule related to connected vessels. Connected vessels are different vessels and different shape, different in shape, different in capacity, different in direction, connected together, which is called connected vessels. Connected vessels like this. If we put a water from here, the water will separate and distribute in all vessels and will move up, and we will note that or observe that the level of water on all vessels has the same level, where all vessels, each vessel has its shape and its a capacity which differs from one to another, but the level of water in all vessels has the same. As why? This is due to if we takes a point at the bottom of the first vessel and another point at the same level at the bottom of the second vessel, and point 3 at the third level, the third vessel, and all points at the same horizontal level, so have the same pressure. Point 1 and 2 and 3 has the same pressure. Why? Because it's a water. A water is a homogeneous fluid, has a constant density, and G is a constant, so it should be, so rho is a constant, G is a constant, and P is a constant, because they have the same level. So well, it should be, it must be, not should be, it must be, H is the same in all vessels. So the level of water in all vessels where its capacity and shape is different, but has the same level due to all points at the same level has the same pressure. So okay. How can we measure the atmospheric pressure? Atmospheric pressure. Torsley, one of the greatest scientists, which built a barometer, the device which used to measure the atmospheric pressure. This barometer consists of a container, a wide container, contains mercury, and a large tube open from one side and closed from the other side. It is not important to be a fixed or has a certain cross-sectional area. This tube is completely filled with mercury. Then Torsley takes the tube and put it upside down in the container without be touching the bottom of the container to give the ability of mercury to move from the tube to container or from container to tube. Torsley notes that the fluid, the mercury, falls down from the tube towards the container, but after a few minutes he found that the mercury inside the tube stopped. When he measured the pressure, the height of mercury inside the tube from the surface of container mercury to the surface of the tube mercury, he found that it is 0.76 centimeter, 76 centimeter. What happened? What happened to B? The mercury stopped at this height exactly as the surface of C. Because the air pressure press the surface of mercury container. So the mercury at the container try to move up inside the tube. Where another a force applied from the weight of mercury inside the tube try to fall down. So there is two forces. The pressure, the atmospheric pressure and the pressure of fluid inside the tube. So the pressure inside the tube more than outer the tube. So the mercury moved down. When the pressure outside the tube equals the pressure inside the tube, the moving of fluid stopped. Means the pressure inside the tube equals the pressure outside the tube. So he said that the atmospheric pressures equivalent the pressure of the weight of 76 centimeter mercury. So the atmospheric pressure equals the pressure which causes from the weight of the container, the mercury, or 76 centimeter mercury. Okay. Atmospheric pressure equals PA, atmospheric pressure equals 1 ATM equal 1 ATM equal 1.013 multiplying 10 power 5 Newton per meter square, equivalent Pascal. So atmospheric pressure equal 1 ATM or 1.013 by 10 power 5 Newton per meter square or Pascal. Each 10 power 5 pascals equal 1 power. So 1 power equal 10 power 5 pascals. So we can substitute Pascal or Newton per meter square by bar. So atmospheric pressure by a unit bar equals 1.013 bars. Equals 0.76 meter mercury and equals 76 centimeter mercury and equals 760 millimeter mercury, which equivalent torr. So 1 torr equal 1 millimeter mercury. It is the unit of measuring atmospheric pressure. How to convert between units? The value like 3 ATM. If we want to change it to pascals, how we can change it to pascals? At first, the atmospheric pressure by ATM equals 1 ATM. And the atmospheric pressure by pascals equals 1.013 multiplying 10 power 5 pascals. If we divided both of them, we'll find the value in pascals equals 3 multiplying 1.013 multiplying 10 power 5 over 1. In general, if we try to convert from a unit to another unit, we'll take the value like 3 multiplying the atmospheric pressure by the required unit as 1.013 by 10 power 5 over atmospheric pressure by the original unit as 1 ATM. In general, if we want to change from a unit to another unit, we'll multiplying the value required to be converted, multiplying the atmospheric pressure by the required unit over the atmospheric pressure by the original unit. Okay, goodbye.